Chemical reactions tend to be controlled by electrons. When we drew Lewis structures, we learned that electrons are located in lone pairs or within bonds. But more generally, we can talk about molecules having electron density in different areas of the molecule. And when we have a Vesper structure, when we have a three-dimensional structure, we can talk about one area or one side of a molecule having more electron density and the other having less. We can talk about the polarity of the molecule. And to work out the polarity of a molecule, there are 3 steps you follow. You draw the Lewis structure, you determine individual bond polarities, and then you either use symmetry or addition of the dipole moment vectors to decide whether or not the overall molecule is polar. We'll start with BF3, which you may remember is one of the exceptions to the octet rule. There aren't enough electrons around the boron. So we've drawn the Lewis structure for BF3. The next thing we have to do is determine individual bond polarities, and to do that we need to know about electronegativities. Using the periodic table, you can determine that fluorine is much more electronegative than boron. So the individual bonds are polarized with the positive side towards boron and the negative side towards the fluorine. We can represent this with a series of arrows. These arrows represent the bond polarities. In each case, the positive side towards the boron and the negative side, the arrow, towards the fluorine. And now we can decide whether or not the overall molecule is polar or not. We can do it 2 ways. We can do it symmetrically. We can say that each of these 3 polar bonds is arranged symmetrically around that central boron, and they're each going to cancel one another out because the magnitude of their dipole moments and the orientation of their dipole moments is exactly canceling one another. Or we can recognize that dipole moments are vectors, and we can use vector addition to determine the overall vector. Vector addition is done tip to tail. When you do the vector addition and you add all 3 of those dipole moments together, you can see that you end up exactly where you started from. And in this case, that means that you have a nonpolar BF3 molecule. The methane, the CH4 example, will be very similar. Methane has a tetrahedral arrangement with 4 electron domains. And just like with the BF3 molecule, all of the bonds are exactly the same, and they're all arranged symmetrically around that central atom. Because of the high symmetry, all of these bond dipoles will cancel when they're added together. And this gives us a nonpolar molecule. The CO2 molecule is linear. It's also very, very symmetric. So again, we have a situation where, due to the high symmetry, all of the dipole moments are going to cancel. In the case of carbon and oxygen, the oxygen is much more electronegative. So you have 2 equal and opposing dipole moment vectors. They cancel if you add them tip to tail, so this is also nonpolar. Water is the first of the polar molecules that we'll be examining. Water has 4 electron domains, 2 bonding and 2 non-bonding. So its electron domain geometry is tetrahedral, and its molecular geometry is bent. The bent geometry means that the distribution of charge within this molecule is not symmetric. You have the lone pairs at the top, and you have the hydrogens at the bottom. In this case, the bond dipoles, when you add them together tip to tail, give you an overall net dipole moment. And if you end up with an overall net dipole moment, you have a net polar molecule. And in this instance, the positive side of the molecule is the bottom side with the hydrogens, and the negative side is the top with the lone pairs of electrons. CHCl3 is also polar. CHCl3 is tetrahedrally shaped. It has 4 bonding domains. In this case, we also have an asymmetry. We have 3 chlorines, but we also have a hydrogen. So we have to, again, find the individual bond polarities and then check to see how those dipole moment vectors add up. In this case, all of the dipole moment vectors are pointed in more or less the same direction. And if you do vector addition with them, you'll find that the overall dipole moment for the molecule all points down. This means that you have a positive side near the hydrogen and you have a negative side towards the chlorines. And you can use this method to decide whether or not any given molecule is polar.